Good evening, students. Today we are going to discuss about the electron spin resonance or electron paramagnetic resonance. So we already discussed all the particles that are electrons and the neutrons and the protons will revolve around their own axis. That is, all the spinning particles will exhibit this resonance phenomenon. What is a resonance phenomenon? The spinning particles will absorb the radiation such as radio wave frequency in the presence of external magnetic field. So this is the phenomenon of any resonance techniques in a spectroscopy. So ESR is related to electron spin resonance technique. It is also known as electron paramagnetic resonance technique. So electron spin value is 1/2. So this electron spin resonance is applicable to valency electrons, that is atoms having single valence electron in the outermost orbit. That is, if there are two number of electrons, then the resultant spin is equal to either 0 or 1. So these particles, these spinning electrons may not orient in the direction of external magnetic field. So compulsorily the atom should possess one unpaired electron in the outermost orbit. So the atoms which are having unpaired electrons in the outermost orbit are called paramagnetic substances. So that's why this electron spin resonance is also known as electron paramagnetic resonance. Paramagnetic means only paramagnetic substances can only exhibit this electron spin resonance. So what is the main important phenomenon inside this electron spin resonance techniques? So let us consider a single valence electron system or an atom or molecule. Then for that electron, the spin value is equal to 1/2. When this electron is placed in an external magnetic field, so we all of us know that Zeeman effect. What is Zeeman effect? The splitting of spectral lines in the presence of external magnetic field. So in ESR also we are placing the atom in external magnetic field. So when this single valence electron is placed in an external magnetic field, each energy state will be split up into two components, which is represented with the letter MS. MS is magnetic spin quantum number. So these single valence electron states are classified or further divided into two states, plus half or minus half, in the presence of external magnetic field. So what is happening when this atom is placed in an external magnetic field? So we all of us know that every spinning particle will possess the magnetic dipole moment. For the electron we have already calculated as minus G beta E into Sz, where G is the Landau splitting factor, beta E is the Bohr magnetron, S is the spin quantum number. When this magnetic dipole moment, which is associated with that electron, is placed in an external magnetic field, North Pole and South Pole, these magnetic dipoles will try to orient in the direction of external magnetic field. That is, there is some interaction between the magnetic dipole moment with that of the external magnetic field. So I am indicated with that the term delta E. Delta E is the interaction energy given by mu dot Bz. So by omitting the negative sign indicates the negative charge of an electron, G beta E, and Sz component is half. I am written as Bg. So if you divide this equation with this H, that is G beta E Bz by H, then what will we get? We know that delta E is equal to H nu. So then what is nu? Delta E by H. So we can calculate the radiation emitted by these spinning particles, so which is nu. This is the main important formula in any resonance technique. So G is the Landau splitting factor, beta is the Bohr magnetron, B is the external magnetic field, H is the Planck's constant. So in the presence of external magnetic field, each spin state is split up into two different states. Ms is equal to plus or minus half. So we have derived delta E is equal to G beta E Bz. So that is, what is delta E? Separation between the two levels. What is the separation? The separation between Ms is equal to minus half to Ms is equal to plus half. This is delta E. So this delta E depends upon G is Landau's factor constant, beta is Bohr magnetron constant. It depends upon the external magnetic field. At a fixed magnetic field, this delta E is constant. If you are varying the external magnetic field, this delta E also changes. If you increase B, the separation between delta E will also increases. So this can be represented in a graphically as, on x-axis I am taking the external magnetic field, on y-axis energy. If you draw the separation between the two lines, that is Ms is equal to minus half, Ms is equal to plus half. As we are from this diagram, what I am showing is, if you increase the external magnetic field, the separation between the two levels will also increases. So that is delta E is directly proportional to B. At a fixed magnetic field, for example, at B naught, delta E is fixed. So what is delta E here? Delta E is equal to G beta E. At this point, the magnetic field is equal to beta. So when the electromagnetic radiation, radio wave made to incident on this molecule, this h nu amount of energy is absorbed by the electron and it is excited to minus half state to plus half state. That is, h nu must be matched with this energy gap, that is G beta E V naught, which is equal to delta E. So this condition is called resonance condition. If h nu is equal to the separation between these two lines, then this radio wave is absorbed by that electron and the electron is excited from Ms is equal to minus half to Ms is equal to plus half state. This condition is called resonance condition. Right. If you draw the graph, if the radio wave is absorbed, if this I am writing again here, the resonance condition is delta E is equal to h nu is equal to G beta E B naught. This is the resonance condition. If the radio wave is absorbed on the graph, if you draw the magnetic field, so if the radio wave is absorbed, we get a sharp spike on the spectrum. So that is, this radio wave is absorbed at a particular magnetic field beta naught. But in your ESR practicals, you got the spectrum like this. So we are not getting the single spike in the spectrum. We are getting two spikes in the spectrum. Okay, why? Because this phenomenon is further explained. So this is the main introduction of electron spin resonance. So actually we need to get only a single spike, but we are getting two spikes. Why we are getting these two spikes means this is because electron nuclear coupling. So this another topic is electron nuclear coupling or hyperfine interaction. So originally what we are getting, so from ms is equal to minus half to ms is equal to plus half state, there is only one transition. So practically we are observing only a single spike. So but practically we are getting two spikes like this. So if you consider the simplest atom, hydrogen. So in a hydrogen atom you will have one electron and one proton. So when the atom is placed, not only the electron but also protons will also interact with the external magnetic field. That means this electron and proton are interacting with the external magnetic field. So that is since electron and proton are very nearer, so there is some interaction between electron and proton. So for example, in hydrogen we have one electron and one proton. For this electron, when it is placed in an external magnetic field, what are the possible ms values? Ms is equal to minus half, ms is equal to plus half. But this electron is interacting with this single proton. So proton will also possess the spin value. So what is its value? It is represented with the letter I called nuclear spin value. It is 1 by 2. When it is placed in an external magnetic field, it will also split up into two components. That is, here this electron spin state is further split up into two different nuclear spin states. That is, mi is equal to plus half and mi is equal to minus half. Only single electron state is split up into two different nuclear states. Similarly, ms is equal to plus half state divided into two different states. That is, mi is equal to minus half and mi is equal to plus half. So here the transitions can be observed between two different electron spin states but with same nuclear spin states. Here the transition is allowed. Important one is here transitions are drawn between two different electron states with same nuclear spin states. For these states, mi is equal to minus half. For this state, mi is equal to minus. Same nuclear spin states but different electron states. Hence, here we can draw one transition from this level to this level. Similarly, for this state, mi is equal to plus half. Here it is also mi is equal to plus half, but different ms values to spin state. So, hence, in the spectrum, we get two spikes separated by constant distance. So, instead of one spike, we are getting two spikes for the hydrogen atom. So, one spike is observed only for single electron with no zero number of protons. So, for one electron and one proton, we are getting two spikes. Next, consider hydrogen molecule ion. So in hydrogen molecule ion we have 1 electron and 2 protons. So for this 1 electron, the possible ms values are minus half and ms is equal to plus half. But for these 2 protons, the nuclear spins are either orient like this, that 2 spins are upwards, either 2 spins are downwards, one spin is up, another spin is down, one spin down and the other spin is up. So here the resultant spin is plus half and plus half, that is 1. Here plus half and minus half and plus half, the resultant spin is 0. Here it is minus 1. So for the 2 protons, the resultant spin is 1, 0, minus 1. So each spin state is further split up into 3 different states having mi values 1, 0, minus 1. This mi is equal to plus half state will also split up into 3 different mi states. They are 1, 0, minus. So we can draw the transitions from 1 to 1, from 0 to 0, from minus 1 to 1. So on the spectrum we are getting 3 spikes by taking external field as a reference, but we are not getting a central spike is not having the intensity of this adjacency, because the resultant spin, in the resultant spin 0, here 2 protons are participating, here also 2 protons are participating, here 4, that is double the number of protons are participating with the resultant spin 0. That is, this central spike is doubler. So we get 1 is to 2 is to 1. The central spike, in central spike, since there are 4 number of neutrons are participating with the resultant spin 0, the central spike is having double the intensities. So for 1 electron and 2 protons, we get the spectrum like this, right? Next, consider CH3 plus ion. CH3 plus ion, which consists of 1 electron and 3 protons. So for 1 electron, same states, ms is equal to minus half and ms is equal to plus. These 3 protons will orient like this, or 2 protons up, 1 down. So there are 3 different combinations like this. So that is 1 proton up, 1 down and up. Here also 2 up and 1 down. Next 1 down and 2 up. Next 1 proton is up, remaining to r down. So here also we have 3 different permutations. So here all the protons may be downward. That is 1 by 2 plus 1 by 2 plus 1 by 2, that is 3 by 2. Here 1 by 2 plus 1 by 2 minus 1 by 2, that is resultant spin is 1 by 2. Here 1 by 2 minus 1 by 2 minus 1 by 2, the resultant spin is minus 1 by 2. All are downwards, that is the resultant spin is minus 3 by 2. That is, we are getting 3 by 2, 1 by 2, minus 1 by 2, minus 3 by 2 resultant spins for protons. So let us draw this APR spectrum for this CH3 plus molecule. That is Ms is equal to minus half to Ms is equal to plus half. We are having only one transition. So if you consider the protons interaction also, three by two, 1 by 2, minus 1 by 2, minus 3 by 2, we got 4 transitions. That is 3 by 2 to 3 by 2. Next 1 by 2 to 1 by 2. Next minus 1 by 2 to minus 1 by 2. Next minus 3 by 2 to minus 3 by 2. Here in this diagram we have drawn the 3 into 3 into 3, that is 9 number of protons are participating with spins plus 1 by 2 and minus 1 by 2. Hence we got the spectrum like this. That is first one and thrice the intensity of that of the first one. Next also thrice the intensity of the first one. Next with the lower intensity. So this is the EPR spectrum for CH3 plus molecule. So for 1 electron and 3 protons, we got 1:3:3:1 like EPR spectrum. Next, if you summarize all these EPR spectrums, how I am summarizing this EPR spectrum? For 1 electron and 0 number of protons, we got only one single spike. For 1 electron and 1 proton, we are getting 2 spikes separated by constant distance. For 1 electron and 2 protons, we got one spike with double intensity, another spike, next spike. For 1 electron and 3 protons, we got the spectrum like this by taking the magnetic field as reference. So this resembles the Pascal's triangle. So what is Pascal's triangle? You all of us know. So 1 1 1, next 1 2 1 1. If you consider this as 0 0, 1 1 here, 1 1 plus 1 2 1. Again we are getting 1 1 plus 2 3, 2 plus 1 3, again 1. So for the next that is for 1 electron and 4 protons, how we get the spectrum? We get 1:4:6:4:1. That is, we got the spectrum like this. So these are the different EPR spectrum of molecules. So from that we conclude that from the EPR spectrum, for any unknown molecule, we can find out what are the number of protons present in that molecule. So if the EPR spectrum is like this, there are 0 number of protons, but there is no ideal molecule which is having 0 number of protons. Next, if we got the spectrum like this, we can say that that molecule will have 1 proton. If we got the spectrum like this, the molecule will have 2 protons. If you got the spectrum like this, the molecule will have 3 protons. If you got the spectrum like this, the molecule will have 4 protons. So in your practicals, for a DPPH molecule, so you got the spectrum like this. That is, this DPPH molecule is having one electron and one proton inside that nucleus. This single peak is split up into two peaks, hence the Landis splitting factor is equal to 2. So you practically calculated this G factor also. This is regarding the electron spin resonance technique.